Okay, we're good. So please round of applause for the last talk of the day.
Hello, everyone. Hello. Yes, that's like that. It's really amazing to see the room full of people, even though this is the last talk, the last session, and the last day of the conference. So thank you and welcome. So this is a collaborative work from my colleagues and supervisor from Athens University of Economics and Business. So all the good part you are seeing going to see today is all belongs to them. All the problems that you may say, what is that? You can point to me. And well, let's start. So what we are going to talk about, we will discuss about smells, code smells, and some earlier speakers have made my job a little easier, so I'll probably skip those parts very quickly. So we'll talk about smells, we'll talk about how people detect smells today, and we'll talk about how we tried to detect smells using deep learning. And I'll go a little bit in technical detail what we did and what kind of experimental setup we put up and what kind of results we got. This is what we are going to do. Sounds good? Great. So before going into that, let me briefly talk about myself and give a disclaimer that I'm not really a machine learning expert like most of you. I'm a software engineering researcher. I'm completing my PhD hopefully in a couple of weeks. So, and these are the topics that I'm mostly working. So, refactoring, smells, code quality, these are the things that I mostly work with. Okay, so let's start with the term smell. Who coined the term smell? Any guesses? Yep.
Should I explain it to?
No, you just say who coined that term. Anybody? No. Not really. Actually, the term came up in the book by Martin Fowler, but it was coined by Kent Beck in 1999 in the famous Martin Fowler's book, because that chapter about smell was co-written by Kent Beck. And they defined that term very casually, like certain structures in the code that suggest or sometimes scream for the possibility of refactoring. And later on, and especially in academic world, many people defined that term much more rigorously, and you can find all the definitions here. If you are interested in the smell catalog, I put together at least the known and common smell, and right now there are 264 smells belonging to different domains and subdomains of software. If you are interested, you can find that catalog here. So let me give some examples before I delve into the detection part. So when we talk about smells, we can classify them based on the granularity, based on the scope, and based on the impact that they make. So the lowest granularity is the implementation smells, which you can detect or you can sense just looking at, for example, a method. So magic number, complex method, or an empty catch block, these are the kind of smells that you can spot just looking at a method. The next granularity is design smells that are mostly at a little higher granularity, and when that kind of smell that you can detect by looking at this, the classes, abstractions, and the relationship among them. So examples are like multifaceted abstraction, when a class is doing much more or realizing much more responsibility, or insufficient modularization, which means, or more commonly known as God class. When you see a software from components and the relationship among them at that granularity, you are and you are detecting smells, you are detecting architecture smells, and these examples are basically architecture smells. God component or feature concentration. Feature concentration is nothing but a component is doing more than one. Scattered functionality is like a responsibility is scattered across multiple components. So how people are detecting so far smells? So there are basically 5 different categories. If we try to analyze all the different smell detection algorithms or the methods available today, there are basically 5 different categories: metric based, rules or heuristic based, machine learning based, optimization, and history based. And most common ones are metrics and heuristics. And what people do normally, this is what people do. So you have source code, and you prepare a source model out of that. Okay, that's not really working. Okay, so you prepare source model, and source model could be anything. More simpler, an example could be AST, abstract syntax tree, and from that source model you compute metrics, and then you apply a certain threshold to classify whether that smell is present in that particular method or class or a component. Recently, some attempts have been made to detect smells using machine learning. And this is, again, a very high-level view what people do when they want to detect smells using machine learning. So you have source code, and you again prepare some sort of a source model. You have a machine learning algorithm. Again, there are different kinds of machine learning algorithms that you may apply. There are some existing examples, especially I'm talking about you have existing examples that you use to train the machine learning algorithms, and you have a trained model, and with that trained model you actually infer the new code, that whether those code snippets or code fragments can be classified as smells or non-smells. I would like to brief about what kind of existing academic work has been done on related to machine learning based approaches. So people have used support vector machines, bias and belief networks, logistic regression, and even CNN. And for first 3 of them, the feature set or the input is matrix, object-oriented matrix typically. And that's basically a double-edged sword. At one end, you are trying to help machine learning algorithm to pick the classification feature very quickly, so that the algorithm can decide whether it's a smell or non-smell. But on the other hand, you are reducing the search space, and so that and you are limiting the capabilities of machine learning or deep learning algorithm by limiting the capabilities of that, because you are now giving only the matrix. So the machine learning algorithm is bound, that can do at best what that metric can represent. If the metric is not representing the feature or the characteristic that is helpful in detecting that smell, then, well, we are not going to get a good classifier. Another related problem, especially in the existing work, is either the validation is, there are many details missing, or if there are details are there, then the validation is on balanced samples. And in the morning also we have seen that when we have a balanced set versus imbalanced set, that can be really drastic change in the performance. If you are representing a realistic case in which you have maybe 1% of classes are smelly and 99% classes are non-smelly, then, and you apply some sort of a machine learning algorithm, and your precision recall curve will be like this. So that's one of the observations that we had. And with this sort of background, these 2 major research questions that we set up for ourselves. The first one is it really feasible or possible to apply deep learning to to detect smells. And if it is possible, then which method is performing superior. And basically we analyze CNN and RNN, and we give inputs in 1D and 2D. So we basically have 3 models to compare: CNN 1D, CNN 2D, and RNN. In the second research question, we are exploring whether transfer learning is feasible. And what is transfer learning? Transfer learning is nothing but a technique where we exploit the commonalities between different learning tasks. So what we are going to do essentially is that we learn a model from one programming language, and then we apply that trained model to another programming language. Okay. So to do this, what we have done, we have a research question, set of research questions that I already talked about. We downloaded source code. Obviously, our first approach is first step is to download source code, and GitHub is the to-go method. So we downloaded C# and Java repositories. We use DesignIte to detect smells in both kind of repositories. We use code split, again our own tools that we have made available. I'll share all the details where you can find all these tools. So we basically are generating code fragments from these big projects. I'll go into each step individually also, so I'll go a little bit in more detail. This is just, I'm giving an overview. And then these code fragments and the detected smell, we basically classify these code fragments into positive and negative samples. And then we tokenize them. After tokenizing, we prefer a pre-processing, which is nothing but removing the duplicates. And then we finally give it to the deep learning models. This is the overall setup that we used. Let me go into a little bit in detail one by one. So we downloaded more than 1,000 repositories containing C# code. We selected 2,500 and downloaded 100 repositories just for validation. We are using Java repositories just for validation, so we just downloaded 100 repositories. And how we selected these numbers, 1,000 and 2,500, we had 8 dimensions: architecture, continuous integration, unit tests, and so on and so forth. So we selected all the repositories that has at least 6 out of 8 positive numbers, favorable numbers in these dimensions, and number of stars at least 5. So we discarded everything which is less than 5. With that, we got these kind of numbers, and we downloaded the code. The second thing we did is that for each project, we need to split the big projects into individual samples, individual fragments. An individual fragment could be a method when we are detecting implementation smells, and a class if we are detecting a design smell. So depending on that, we basically split the code into either method or class, and we put them in a separate files. Same thing we did for the Java. Next step is smell detection. We use DesignIte, and for both DesignIte C# for C# code, and for Java, DesignIte Java for Java code, and detect all the smells that can be found in the code. And by the way, DesignIte is a tool which can detect 19 design smells, 7 architecture smells, and 11 implementation smells. And similarly, DesignIte Java version is also picking it up to that level. You can download these tools, and again, at the last slide, I will share all the links to you. So we know what kind of smells a project has, and we know all the code fragments. So with these 2 pieces of information, we classify these code fragments either through a positive sample or to a negative sample. After that, we use tokenizer. A what tokenizer does basically takes a code fragment and converts into integer tokens, a set of integer tokens. And to do that, and in that context, there are two important things to mention. Tokenizer defines specific ranges for specific tokens. For example, all the reserved keywords are always assigned the same token. And all the user-defined symbols are also specified or assigned a specific set or a specific range of tokens. Another fact about tokenizer is that right now it supports 6 languages, including C# and Java, which was our subject systems. It looks like this. So if you have a very small method, then if you tokenize this method into 1D, it will look like a 1D vector. And if you have a 2D matrix, then it looks like something like this. And again, it's important to go a little bit in more detail and see how we prepare the data, how we train the model. So that's why I'm showing you a very specific example of a smell. So this is a approximately 5,000 number of positive samples we have for a smell, and more than 311,000 negative samples. So this is you can see that it's a highly imbalanced data. And that we split into 70-30, 70 for training and 30 for validation. And what we do, obviously we have 3,000 and we have a split, 70-30. And for training, we take this positive part and this negative part. And similarly for the evaluation, we do the same. Here when we train the model, we do balanced training, which means that we have equal number of positive and negative samples. So what we do, basically we discard anything extra that we have with this particular part, the negative part. So we have equal number of positive and negative only for training. For evaluation, we keep the ratio as it is. We don't change it. And all the results that I'm going to show it on the real world evaluation. And we selected 4 smells. All 4 smells are different kinds of smells. 3 are implementation and 1 is design. So the complex method is the method that has a high cyclometric complexity. Magic number is a numerical literal, is used in the expression without explanation. Empty catch block is a catch block of where the exception, there is nothing written in that catch block. And then multifaceted abstraction is a kind of difficult to detect smell, and that's why we chose it, because it is a very different from the rest of 3, and because it has a semantic meaning. You can't detect a multifaceted abstraction just looking at the code. You need to understand what it does, because what it means is the cohesion of the class is low. So these are the 4 smells that we chose, and now let's talk about what we did, what kind of CNN model or architecture we prepared with the CNN. So you can see that we have convolution, batch normalization, and max pooling layers, and these layers are repeated in the sense when we experimented with number of deep layers, and when we say deep layers, we only refer to these number of deep layers 1, 2, and 3. So if deep layers are equal to 3, which means we repeat these 3 times. And we did a kind of a grid search, which means that we chose different kind of hyperparameters, and we experiment with all the permutations and combination. And we use dynamic batch size depending on the input sample size. So if the number of samples are very small, then we use the smaller batch size, but if the number of samples are very large, then we use the higher number of batches. For regularization, we use early stopping with patients 5 so that we don't overfit, and model checkpoint along with that. And some other configuration you can see here that dropout layer has a 0.1 dropout, and the dance has, the output is 32 with the ReLU activation and so on and so forth. Similarly, for RNN, we have LSTM layer, and before that we have embedding layer. And when we have a number of layers, multiple deep learning layers, we basically repeat this LSTM layer. Again, we have different kind of hyperparameters and dynamic batch size and similar size, similar callbacks. Although we use patients too, because it is very expensive to train RNN model, and if time permits, I'll talk about that in a little bit more detail. So essentially, what we did is we had 2 phases. In the first phase, we did a grid search with the different kind of parameters, configurations. So we had 144 configurations for CNN and 18 for RNN, and we kept validation set 20% aside for the first phase. In the second phase, when we know which configuration works the best, we run it again with the validation 0, obviously. And we performed all the experiments on GRNet facility, which is a Greek supercomputing facility, with the 1 GPU and 64 GB of memory. So what we got? What we got is, before I go into what we got, when we were, and I said initially that we started without any knowledge of machine learning. So the first thing that I did is figuring out accuracy. So I was computing accuracy, and the first time when I run the model, and I got 99% accuracy, and I was jumping, and I told my supervisor, see, 99%. And he looked at me, you have imbalanced data, and huge imbalanced data. Obviously, you will get 99%, even if your model is just predicting 1 or 0. You'll get that. So then we learned that, okay, that's not the right way. So the first thing we added is ROC AUC. So this is the kind of ROC AUC we got. So area under curve, basically this is what we got. So it's crossing 80% in some cases, and the lowest end it's 50% or something like that. However, we again realized that this is not the right way. We should do precision recall and precision recall curves, and this is what we got for precision recall. And basically we summarize precision recall into F1 F measure to have a comprehensive 1 number. So you can clearly see that some of the smells, these deep learning architectures that we design can pick it up, but some they can't. And the reason in general F1 is low, because we have low precision. And why we have low precision? Because we are predicting false positives, a lot of false positives. So, well, we can optimize that whether we want high precision and recall, and probably you know better that precision and recall always have a trade-off. So if we want to get higher precision, we can have to compromise on the recall and vice versa. So this is what the first result, and we go into a little bit on detail that whether CNN versus RNN. So whether CNN is better or RNN is doing better in our case. And we see if you look at the maximum F1, there is hardly any difference. Even if we plot all the cases, then also it's not decisively, we cannot say that whether CNN is better in our case or CNN 2D is better. We also did comparison between CNN and RNN. I would not consider this because in all the cases, in all the three models, the performance was very low, so 0.004 or something. So, which means that it's not really fair to compare 0.004 and 0.006 because it's a very it will bring the multifold difference. However, here when RNN can detect something, it's doing very good. In case of complex method, it's not doing that great because probably it cannot capture the structural property of the method. However, in other cases, in these two cases, probably RNN is picking up that feature, and that's why it's doing much better than the rest of the two models. Another experiment that we did is it beneficial to increase number of deep layers? And what we found is, well, for the second layer, maybe we get some boost up. However, it starts decaying, or at the best, it will not change anything. So again, when we are applying deep learning, we need to see that whether increasing number of layers, whether it is beneficial or not, or we are just increasing our training time. This one is even interesting. So I would repeat what we did here. So we trained the model in C#. However, we applied that trained model to Java samples to see whether the same trained model, how fairly or how good it is to classify Java samples into smelly and non-smelly code. And this is what we found. And again, it is something similar trend, but if you compare this direct training versus transfer learning, you will see that transfer learning is doing much better. So the model trained on C# is better in detecting smells in Java code rather than its own code, which is kind of surprising, and I'm still looking why it's happening, honestly. But this is what we got. So this is what it is. Let's conclude. The first conclusion is that it is feasible to make deep learning model learn to detect smells. Obviously, which smell you are detecting and the performance varies, and we can do much more. That's a separate thing. Transfer learning is also feasible. We have seen that it is feasible. So what it implies that if you have a very good tool for one language, one programming language, then you don't have to invent or write the tool for other programming languages, at least similar programming languages. You train the model and you apply the model to other programming languages. And obviously there are many possibilities for improvement. We can improve performance, we can add more smells, different kind of smells, and this is, I believe this is just a start, and there are many things that can be built over it. So these are some relevant links. As I promised, you can download all the source code and data here. I made it open source today morning. You can download the design for C# here, and for academic use it's free. For Java, it's open source project. You can do whatever you want. Code Split is again, this Java version is open source. You can download and you can play with that. And for C#, you can download freely without any charge. Tokenizer is another tool that we have offered, and you can again use it. It's an open source project. Feel free to use it. Okay, thank you. If you like stickers, I have some stickers, some fancy stickers. Please feel free. Yes, please. Yes.
So I'd like to ask, what is the exact input to the evolution line?
Okay, what is the exact input to the convolution layer? Okay, so as you can see the architecture, I mean we have defined, and before giving to the deep learning model to the whole models, we convert source code into tokens. So yes, tokens, integer tokens, but we have a NumPy array basically, which individual element is basically integer token. And in 1D CNN 1D, we have each input, or for example, each method is a single vector, 1D vector. In 2D CNN 2D, we have the matrix. So each input sample is a matrix, 2D matrix. Yes, please.
How does the tokenizer work? What do you remove from source code?
It doesn't remove, I think. It's only the white spaces it removes. So the question is that how does the tokenizer work, and what it removes from the source code. So I think it doesn't remove anything. It just removes white spaces. And for each token, for example, public, if it is a reserved word, there is a set of tokens assigned to it. If it is a user-defined symbol, then there is a range of tokens in which assignment will be made. And if it is a numerical literal, again it's a range of tokens which will be assigned to it. So something like that.
On framework dependent codes, how do you for example, if it's a Spring or something.
Framework dependent code. Okay. The question is how it will work on framework dependent code. I don't see any difference between framework dependent code or any, otherwise, but we have not tested it, so we have to. This is a very first attempt right now, so it's maybe we can do that later.
Day-to-day development area, we use framework pattern industry. It's basically a Java program, plain Java program. That's what that will change to Java.
I don't think that will impact anything, because whatever code you provide, and anyway, it's the scope is very limited for the scan. So it's for implementation it's just one method. So it's just looking that method. Please.
So what do you think are the main challenges to scale this to more complex smells, like scattered functionality or things that are harder to solve?
Repeat the question and move back a little bit there.
Okay. The question is, what are the challenges if we want to extend this work to more involved smells, more complex smells? For example, scattered functionality. It is difficult. It is difficult because our goal was that we will not give the processed input to the model. We want to give model as close to the raw source code. We just tokenize it and remove the duplicates, but we didn't do anything else which normally referred as feature engineering. We didn't do that, and that's one of the aim. We intentionally didn't do that because this is how we want to process it. But if we want to go a little bit in detail and more involved smells, and which we have seen in the multifaceted abstraction, it's not really easy. The whole characteristic of the smell is not captured really, and the model cannot capture, even we given a training size of 10,000, cannot capture that. That is one possibility, but probably we need to do some sort of, or mix or introduce relevant features, or give relevant features to help the model to detect better.
Last question.
I'm not that really technical because I stopped coding 5 years ago. So when is it useful to have this deep learning algorithm? The accuracy of natural language processing is above 95% right now to detect the smell. When do you consider it useful? At what accuracy level is the goal for the industry?
The question is that is it ready for the industry? If I summarize it, at what level?
Accuracy is it useful for us to?
okay, for the industry, what kind of accuracy will be needed to,
Yeah.
so that we can say, okay, now it's ready for industry?
Yeah.
That's difficult to answer, but in the morning, one of the sessions we say that the precision is really important for this kind of analysis. So if we have a precision or lower precision, like less than 70-80%, then people will reject it very outrageously. So it must have something decent precision, and because this is not really a life-threatening, if we miss something, it's not life-threatening. So we can compromise on precision, but we cannot, recall, but not on precision. Because otherwise, if precision is very high, which means false positives are very high, which means if precision is low, then false positivity is very high, which means people will say, out of 10, only 1 is useful. I don't want to use it. So a decent percentage could be at least 80, 85. There is no gold rule for that, but something like that.
Great. So thank you very much.